Radio astronomy emerged from an unexpected discovery in 1932 when Karl Jansky, an engineer at Bell Labs, detected radio waves from the Milky Way while investigating interference in transatlantic communications. This revelation laid the foundation for radio astronomy, proving that celestial objects emit radio waves. Development and expansion 1940s–1990s. World War II influence. Radar technology advancements during the war accelerated radio astronomy research. First dedicated radio telescopes. Grote Reber, an amateur astronomer, built the first radio telescope in 1937, a 9.5-meter parabolic dish in his backyard. Post-war, radio astronomy flourished, leading to large interferometric arrays and national observatories. Major discoveries. Identification of radio galaxies like Cygnus A and Virgo A. Detection of pulsars by Jocelyn Bell Burnell in 1967, initially dubbed little green men, due to their precise signals. The term, little green men, LGM, was humorously used by Jocelyn Bell Burnell and her colleagues when they first detected pulsars in 1967. The radio signals were so precise and regular, pulsing at exact intervals, that they initially considered the possibility of an artificial origin, perhaps from an extraterrestrial civilization. However, further analysis revealed that these signals were coming from rapidly rotating neutron stars, which were later named pulsars. The term LGM-1 was used for the first detected pulsar, but it was soon understood to be a natural astrophysical phenomenon rather than alien communication. Mapping of cosmic microwave background radiation, supporting the Big Bang theory. Modern space-age radio telescopes. Very Large Array, VLA, USA. A27 dish interferometer used for deep space observations. FAST, 500-meter aperture spherical telescope, China, the world's largest single-dish radio telescope, aiding in pulsar detection. ALMA, Atacama Large Millimeter, Submillimeter Array, Chile, a high-resolution array studying star formation and planetary systems. Square Kilometer Array, SCAR, Global Project, a next-generation telescope designed to revolutionize radio astronomy with unprecedented sensitivity. Radio telescopes have transformed our understanding of the universe, revealing black holes, exoplanets, and cosmic phenomena beyond optical telescopes' reach. The UTI Radio Telescope, ORT, is a fascinating piece of engineering and scientific ingenuity. Located in Mathurai, near Ooty, Tamil Nadu, it is part of the National Center for Radio Astrophysics, NCRA, under the Tata Institute of Fundamental Research, TIFA. The idea for a radio astronomy group in India was proposed in 1961 by 4 radio astronomers, M.R. Kundu, T. Krishnan, T.K. Menon, and G. Homi Bhau, a visionary scientist, supported the initiative, leading to the establishment of the Radio Astronomy Center, RAC, at Ooty in 1966. The ORT was completed in 1970, with its first observations occurring that same year. It was upgraded in 1992, significantly improving its sensitivity. As of 2017, the ORT has been undergoing a major upgrade to form the Ooty Wide Field Array, OWFA, enhancing its capabilities for heliospheric studies and intensity mapping. The ORT is a 530-meter long and 30-meter wide cylindrical parabolic antenna. It operates at 326.5 MHz with a maximum bandwidth of 15 MHz. The reflecting surface consists of 1,100 thin stainless steel wires supported by 24 steerable parabolic frames. The telescope has an angular resolution of 2.3 degrees times 5.5 feet, declination. The ORT has been instrumental in interplanetary scintillation studies since 1970. It has contributed to lunar occultation observations, with the first source 4C22.21 observed on February 18, 1970. It has been used for studies on pulsars, solar wind, recombination lines, and protogalaxies. Protogalaxies are vast clouds of gas that serve as the precursors to fully formed galaxies. They emerge from the gravitational collapse of density fluctuations in the early universe, marking a crucial stage in cosmic evolution. Formation and evolution. Initial stage. The universe begins with a nearly uniform distribution of matter. Over time, dark matter clumps together, pulling in gas and dust. Star formation. Within these gas clouds, the first stars ignite, shaping the structure of protogalaxies. Mergers and growth. Small protogalaxies collide and merge, forming larger galaxies through hierarchical assembly. Observing protogalaxies. Due to the great distances, protogalaxies are difficult to observe. Advanced telescopes like the James Webb Space Telescope, JWST, help astronomers study their properties. Spectroscopy reveals the chemical composition, temperature, and motion. Protogalaxies are essential for understanding how galaxies like the Milky Way formed. The history of ORT and GRAPES 3. From the origins of radio astronomy. The birth of radio astronomy. Radio astronomy began in the 1930s, when Carl Jansky, an engineer at Bell Labs, discovered radio waves coming from the Milky Way. This marked the first detection of cosmic radio emissions, leading to the development of radio telescopes. By the 1940s, pioneers like Grote Reber built the first dedicated radio telescope, laying the foundation for modern radio astronomy. The Ooty Radio Telescope, ORT, located in Tamil Nadu, India, was conceived in the 1960s by Govind Swarup, a visionary Indian radio astronomer. It was designed to study interplanetary scintillation, a phenomenon that helps map the solar wind and distant radio sources. Construction. Completed in 1970, ORT is a 530-meter-long parabolic cylindrical telescope, mounted on an equatorial system to track celestial objects. Scientific contributions. ORT has played a crucial role in studying pulsars, quasars, and solar wind dynamics, contributing significantly to heliospheric research. Unique design. Unlike traditional radio telescopes, ORT's equatorial mounting allows it to scan the sky efficiently, making it ideal for long-term observations. The GRAPES 3 experiment. The GRAPES 3, Gamma-Ray Astronomy PEV Energies Phase 3, experiment, located in Ooty, is a cosmic ray observatory operated by the Tata Institute of Fundamental Research TIFR, in collaboration with Japanese institutions. Origins. Cosmic ray research in UTI dates back to 1955, when B.V. Srikantan initiated experiments at the Cosmic Ray Laboratory, CRL. Development. The GRAPES 1 experiment evolved into GRAPES 2, eventually leading to GRAPES 3, which officially began in 2000. Scientific goals. GRAPES 3 studies high-energy cosmic rays, the NE in the cosmic ray spectrum, and solar storms, using an array of plastic scintillators and a large area muon detector. Connecting ORT and GRAPES 3. Both ORT and GRAPES 3 contribute to astrophysical research, albeit in different domains. ORT focuses on radio astronomy, while GRAPES 3 explores cosmic ray physics. However, their shared location in UTI and their historical evolution within India's scientific landscape highlight the country's contributions to space and astrophysical research. The GRAPES 3 experiment, Gamma Ray Astronomy PEV Energies Phase 3, is a cosmic ray research project located in UTI, India. It is operated by the Tata Institute of Fundamental Research in collaboration with Japanese institutions like Osaka City University and Nagoya Women's University. What does GRAPES 3 study? GRAPES 3 is designed to investigate high-energy cosmic rays using an air shower detector array and a large area muon detector. Some of its key objectives include studying the origin, acceleration, and propagation of cosmic rays beyond our galaxy. Investigating the NE in the cosmic ray energy spectrum, a mysterious drop in cosmic ray intensity around 10 to the power of 5 eV. The NE in the cosmic ray energy spectrum refers to a sudden change in the slope of the spectrum around 3 to 4 peV, peta-electron volts. This feature marks a transition in the way cosmic rays propagate and interact with astrophysical environments. Why does the NE exist? Cosmic rays follow a power law distribution, meaning their intensity decreases as energy increases. However, at the NE, the spectrum steepens, suggesting a shift in the dominant acceleration or propagation mechanisms. Some leading explanations include galactic origin limit. Cosmic rays may struggle to be confined within the Milky Way beyond this energy, leading to increased leakage into intergalactic space. Supernova acceleration limit. If supernova remnants are the primary accelerators of cosmic rays, the NE could indicate the maximum energy they can impart to particles. Single source hypothesis. Some researchers propose that a nearby supernova remnant could be responsible for the sharp cutoff. Rigidity-dependent cutoff. Heavier nuclei, like iron, may experience a NE at higher energies, approximately 10 peV, supporting the idea that cosmic ray acceleration depends on charge-to-mass ratio. Observational evidence. Experiments like GRAPES 3, Cascade, Tibet 3, and LHAASO have studied the NE extensively, refining our understanding of cosmic ray composition and propagation. Some recent findings suggest an ankle-like structure at approximately 9 peV, possibly linked to iron-rich cosmic rays. Exploring the production of ultra-high-energy cosmic rays, approximately 10 squared eV, in the universe. Conducting multi-TeV gamma-ray astronomy to study neutron stars and other compact objects. Examining the Sun's role as an accelerator of energetic particles and its effects on Earth. How does it work? GRAPES-3 uses plastic scintillators to detect charged particles from extensive air showers produced when cosmic rays interact with Earth's atmosphere. It also has a muon detector covering 560 square meters, which helps study cosmic ray acceleration in different astrophysical settings. The origin of radio astronomy and the detection of muons in the 1930s were independent discoveries, but they share a fascinating connection through cosmic rays. Radio astronomy. 1932. Karl Jansky discovered extraterrestrial radio waves while investigating static interference for Bell Labs. His work laid the foundation for radio astronomy, revealing that celestial objects emit radio signals. Muon detection. 1936. Carl Anderson and Seth Neddermeyer detected muons in cosmic ray experiments. Muons were initially mistaken for Yukawa's predicted mesons, but later classified as leptons. The connection. Both discoveries stemmed from cosmic ray studies. Jansky's radio waves and Anderson's muons were indirect evidence of high-energy astrophysical processes. Cosmic rays, originating from supernovae and other energetic cosmic events, produce muons when they interact with Earth's atmosphere. Radio astronomy later helped study cosmic ray sources, linking these two fields. Cosmic muons have several fascinating applications across science and technology. Muon tomography. Imaging large structures. Used to scan volcanoes, pyramids, and nuclear reactors by detecting muons that pass through them. Helps uncover hidden chambers in archaeological sites. Particle physics and fundamental research. Muons are studied in high-energy physics to understand fundamental forces. Used in experiments like Muon G2, which tests quantum effects in particle interactions. Cosmic ray studies and astrophysics. Muons help scientists study cosmic rays and their impact on Earth's atmosphere. Used to investigate dark matter and high-energy astrophysical phenomena. Industrial and security applications. Muon detectors can scan cargo containers for hidden nuclear materials. Used in civil engineering to monitor the stability of large structures. Medical and biological research. Muons contribute to radiation exposure studies, helping understand their effects on living organisms. The UTI Radio Telescope, ORT, is a cylindrical parabolic array rather than a single parabolic dish. Its structure consists of 24 steerable parabolic frames supporting 1,100 stainless steel wires, which form the reflecting surface. This design optimizes ORT for scanning large portions of the sky while maintaining a fixed north-south orientation, making it highly effective for interplanetary scintillation studies. Interplanetary scintillation, IPS, refers to the rapid fluctuations in radio signals from distant celestial objects due to density variations in the solar wind. It is similar to how stars appear to twinkle in the night sky, but instead of visible light, it affects radio waves. The solar wind, composed of charged particles, moves outward from the sun. As radio waves from distant sources, like quasars, pass through these turbulent regions, their intensity fluctuates. By analyzing these fluctuations, scientists can measure the speed and density of the solar wind. IPS is used to track solar wind streams and predict space weather. It played a role in the discovery of pulsars, as astronomers studying IPS noticed unusual signals that led to their identification. IPS data is used in space weather modeling, helping forecast geomagnetic disturbances. Unlike traditional parabolic dish telescopes, ORT's elongated shape allows it to detect signals from multiple sources simultaneously as they move across the sky due to Earth's rotation. The UT Radio Telescope, ORT, is located at approximately longitude 76.7 degrees east and latitude 11.4 degrees north, near Uti, Tamil Nadu, India. Slope of ORT Hill. ORT is built on a north-south hill slope, which is aligned with Earth's rotational axis. The slope of the hill is equal to the latitude of the site, approximately 11.4 degrees, allowing the telescope to function as an equatorially mounted instrument. This unique positioning enables continuous tracking of celestial objects without requiring complex alt-azimuth adjustments. Noise filtering in the UT Radio Telescope, ORT. The UT Radio Telescope, ORT, employs several techniques to filter out unwanted noise and enhance the clarity of astronomical signals. Since radio telescopes operate at low signal strengths, they must effectively eliminate interference from terrestrial sources, cosmic background radiation, and instrumental noise. Filtering techniques used in ORT: bandpass filtering, adaptive noise cancellation, interferometric techniques, polarization filtering, digital signal processing, DSP.